start on time as well. Hi, everybody. My name is Brian Skinner. I'm assistant professor at Ohio State. And today I want to talk to you a little bit about some really interesting data that's about the transition between a Fermi liquid and a Wigner crystal at zero magnetic field. In general, in this talk, I'm going to keep it pretty informal. Please feel free to just unmute yourself and interrupt me as we go along. I'm going to hide lots of the Zoom controls and stuff, so I won't see it I probably won't see it if you just put a message in the chat or something. But if that happens and someone sees it, feel free to stop me so I notice it. Otherwise, just unmute yourself and we'll have fun as we go. Okay, so like I said, I'm going to talk to you about some mysteries near the Wigner crystal transition. And this is really the work of Joe Falson, who's in the audience, assistant professor at Caltech. This is really an experimental talk that I'm giving. And actually, I should probably just start by acknowledging this is a weird talk for a theorist to give. You know, usually when you're a theorist, you give a talk that discusses theoretical work that you yourself have done, and you try to focus on explaining something that is newly understood. And I'm going to do the opposite in just about every sense. I'm going to give an experimental talk about experimental work. And I didn't do it, Joe did it, along with some of his collaborators. And what I really want to focus on is not providing understanding, but trying to highlight what are the sharp mysteries that are implied by the data, and hopefully help focus our effort on things that need to be explained. So, okay, like I said, this is mostly Joe's work. You can read about it in this archive reference. I also benefited very much from conversations with Inti Sodemann, who's another theorist at Dresden. And then we had conversations with lots of other people who really helped us sort of put these results in context a bit, and that includes Igor Leiner, Ilya Gruzberg, Steve Kivelson, Boris Narozhny, Boris Spivak, and Boris Klaus. Okay, so I should probably start by saying a little bit about what this material is that we're studying. So the goal of this talk is to study the two-dimensional electron gas, which in a theoretical sense is just electrons living in a two-dimensional plane with a neutralizing background. But in fact, you have to put it in some kind of material platform, and the material platform that we use is zinc oxide. So zinc oxide is just a bulk three-dimensional crystal, white in color. You use it to make white paint or sunscreen or something like that. And at atomic level, what it looks like is you have these oxygen ions and zinc ions arranged in a structure like this. And within the unit cell of the crystal, you have a built-in polarization. So like an electric dipole moment that say points this way. Now, the clever idea here that Joe and his collaborators have been working on is that you can just replace in a particular plane of the crystal, say this red plane. So as you grow the crystal in some particular plane, you replace a bunch of the zinc ions with magnesium ions. Now, magnesium is also divalent like zinc, so naively, it wouldn't make any difference. But it happens that the magnesium ion has a very slightly different radius than the zinc ion. So 86 picometers versus 88 picometers. And what that means is that it slightly distorts the unit cell of the crystal. And consequently, there's a discontinuity of the polarization as you move through that plane where the zinc ions live. And that discontinuity of the polarization leads, as you might remember from sort of undergrad electrostatics, whenever you have a discontinuity of polarization, that leads to a sheet of charge. And that sheet of charge draws in electrons, and the electrons live in that plane. So now you've sort of formed, by just polarization discontinuity, a two-dimensional plane containing electrons, and they're sort of trapped in a quantum well that's relatively narrow. This is a sort of different idea than is usually used to make two-dimensional electron gases that involve sort of explicitly creating an alloy of different materials or adding dopant atoms that give up their electrons. And the idea is that this method can be somehow less disordered than some of those other ones. So there's been a decade of work that's gone into this by now, and they can show that you can sort of change how many electrons, the concentration of electrons that live in that plane, by changing how much magnesium you put in the plane. Okay, so this plot is sort of a summary of a decade plus of work of material improvements. What's plotted here is the mobility, which is basically how much current you get per electron, which is sort of a measure of the cleanliness of the system. And what you're seeing is that over the last decade or so, the cleanliness of the material, the mobility has improved by more than 2 orders of magnitude, so that the most recent iteration of it has mobility in excess of 1 million, which is 1 million centimeters squared per volt second, and there are relatively few material platforms that can achieve that. And here's some of the key references here. We're going to focus today on this sample right here. And what you're seeing has very high mobility that falls really abruptly as you approach some critical density. And I'm going to talk a little bit more about why it's falling, why its sort of ability to conduct current is very good until you get to some critical density in a second. Okay, but if you're a theorist like me, the upshot really is that zinc oxide just seems extremely close to the ideal 2D electron system, and it doesn't have a lot of the complications that other platforms have. For example, you have a single valley of electron carriers, by which I mean you don't have carriers at one pocket of momentum and a different one. It's just in one valley. The effective mass looks quite isotropic. It has the same mass in all directions, about 0.3 electron masses. That's 0.3 times the bare electron mass, which is relatively large for the system, and that helps us as well. The quantum well is quite narrow. It's only about 5 nanometers, and you should compare that to the typical spacing between electrons. And where we're going to work, the typical spacing between electrons is about 100 nanometers. So this thing is relatively close to an ideal two-dimensional system. And like I said, the mobility is very high. Okay, so this talk is really going to be about the Fermi liquid to Wigner crystal transition, or it's going to be about what happens in the vicinity of the Fermi liquid to Wigner crystal transition. And let me just remind you as a bit of background, well, what a Wigner crystal is, what that transition is. So normally when we think about a two-dimensional electron gas or an electron gas in general, you imagine as you add electrons, filling them in such a way that minimizes the total kinetic energy. So you put an electron in the lowest kinetic energy state, then you put the next one in the next highest, the next one in the next highest, and so forth, given, as dictated by the Pauli exclusion principle. And after you've done this many times, you find that the typical kinetic energy per electron is of order h squared n over m, where n is the density of electrons. So if I write that as instead of in terms of the density n, I write that in terms of the typical distance between electrons r, then I'll find that the Fermi energy goes like 1 over r squared. Now, when we're talking about this state, we're sort of imagining that the electrons are non-interacting, and we're just trying to minimize the kinetic energy. Now we can compare that to the typical repulsive energy between electrons, and it's of order e squared over r, where r is again that inter-electron spacing. Now, if r is very small, which means the density is high, then this Fermi energy is very big compared to the interaction energy, and that sort of state that tries to minimize the kinetic energy is a good way to think about it. But in the opposite limit, where the density is very low and this r is very, very big, what you'll notice is that this interaction energy is much, much larger than the Fermi energy. And in that situation, what you might think is that the electrons are going to want to minimize their interaction energy rather than their Fermi energy. So in other words, this Coulomb energy dominates at large r, and the state that you start, the way you think about your electron gas should not be the one with minimal kinetic energy, but it should somehow be the one with minimal interaction energy. So this was first noticed by Eugene Wigner in 1934. This paper came out, it's only 6 years after Bloch's theorem, which taught us how to think about what metals are. So this is pretty far seeing. And he points out, this is just the abstract of his paper, he points out that in fact, if you want to think about what is the interaction energy of electrons, you have to account for the fact that they repel each other, try to keep as far apart as possible, so that the wave function that describes the electrons will not just be that of a normal Fermi gas, it'll be different. And in fact, he points out that if you're in the limit of very low density, you can think about the situation where electrons have zero kinetic energy. And in that state, the ground state that they want to adopt will look like a crystal, some regularly spaced arrangement where they avoid each other as effectively as possible. And in 2 dimensions, that looks kind of like this. You end up with a triangular lattice of electrons localized at specific sites. And in this way, they're maintaining as large distance from each other as possible while still having a particular well-defined density. Okay, so if you just take the ratio of these things, you'll get this dimensionless parameter that's called RS. You can think of RS as the typical distance between neighboring electrons divided by this material parameter called the Bohr radius, which in zinc oxide works out to be about 1 nanometer. And the limit where electrons crystallize would correspond to this dimensionless parameter RS being very large, much bigger than 1. Now, this is a completely classical picture, just classical point charges. If you remember quantum mechanics, what it'll tell you is that, in fact, each electron sort of looks like a harmonic oscillator sitting in the confining potential created by its neighbors. So this electron is surrounded by, say, 6 neighbors. Those neighbors make an electric potential that has a minimum at the position of the Wigner lattice. And now you can think that the electron wave function is sort of a harmonic oscillator sitting in that potential minimum. And you can convince yourself that at very large RS, the typical size of that harmonic oscillator wave packet, or that harmonic oscillator wave function, is much, much smaller than the spacing of the Wigner lattice, so everything is self-consistent. Okay, so this problem of how an electron liquid turns into a Wigner crystal has been studied for a long time, and it turns out that if you really want to pinpoint where it happens, it's a tricky calculation. But the sort of state-of-the-art calculation looks kind of like this. So what you're seeing here is energy on the y-axis, and this parameter RS on the x-axis, and you should think that lower density is sort of the right here. There are a lot of different lines here that correspond to the energy of different states. I just want you to focus on this red line, which is the energy of a Fermi liquid. So this is the energy of just a liquid of electrons that do not have any spin polarization. And what you can see is that this state is the lowest energy up until the RS equals 30, a little above 30. And then some other state is the lower energy one. And these two lines, the blue line and the black line, describe Wigner crystal phases with slightly different arrangement of the spin. So the black line is one where all the spins are polarized in the same direction. And the blue one has some kind of alternating arrangement of spins. I'm not going to make a big difference between these two. What I really want you to take away from this at the moment is that the best theoretical prediction that we have at the moment is that you should undergo a transition from a liquid to a crystal phase of electrons somewhere around RS equals 30, a little above 30. This is just like a freezing transition, similar to water freezing into ice. But it's not with temperature, it's with density. Okay, so I should probably just do a little bit to give some context. Identifying Wigner crystallization in a really sharp way has been a notoriously difficult problem in 2D electron systems. And that's because the crystal happens at very low electron density. But when the density is really low, all the energy scales are pretty low. The interaction scale is low, and it's easily overwhelmed by other things. So some material disorder that makes a random potential, it screws up your Wigner lattice, or finite temperature. The temperature is too high and the crystal melts for thermal reasons. So there's a very long history of trying to find it, and claims and false claims of Wigner crystallization going back 40 years. And I'm not going to make any attempt to summarize that, but there's a very nice Reviews in Modern Physics article that goes through some of that. Actually, for a very long time, the premier way to see a Wigner crystal was electrons floating on liquid helium. So you just have a bath of liquid helium, and you really just drop electrons on top of it, and they float just above the surface. And this was a way to get low electrons with almost no disorder, and no weakening of the Coulomb interaction by some dielectric environment. Actually, your dominant source of disorder comes from physical ripples on the surface of the helium, but that's been realized since 1979. Maybe a little bit later, it was realized that you could also get a Wigner crystal by just putting everything in a really strong magnetic field. So strong magnetic field, electrons turn tight cyclotron orbits, and there's sort of no kinetic energy anymore to compete with. And then the Coulomb energy is the only game in town. And it was understood that at big enough magnetic field, the electrons would crystallize in this situation as well. And that's been realized for a while. Sorry, this is the first theory paper I know about this, but there are many, many papers about Wigner crystallization in strong magnetic field, which is not the subject I'm going to talk about today. Actually, very recently, there have been two pretty exciting papers that have seen what looks like Wigner crystallization in a 2D electron system without a magnetic field. And these are in these transition metal dichalcogenides. I think this was molybdenum diselenide. And there were two different papers that were quite nice. One of them seems to see a Wigner crystallization, and the sharp signature they see is a sort of Umklapp scattering, so scattering by a lattice by a crystal lattice of electrons. And they can see this Umklapp scattering emerging below the Wigner crystal transition. There was also another, released at the same time in the same journal. There was a nice paper that looked at bilayer Wigner crystals, and they could see something that looked like locking of the two relative to each other. Anyway, I don't want to talk about these too much, but I just want to say that these were both optical studies that look like real realizations of the Wigner crystal. But what I want to focus on today is transport. So I want to talk about just the resistivity of it, the resistance of a two-dimensional electron system near the Wigner crystal transition. And in particular, I'm going to talk about what happens in zinc oxide near that apparent transition in terms of the resistance as a function of three parameters: the electron density, the temperature, and the degree of spin polarization, which we can tune separately with an in-plane magnetic field. Okay, so here's what happens when you measure the resistance as a function of temperature and at different densities. So here are different curves. The bottom curve corresponds to the highest electron density. This is about 2.5 times 10 to the 10 electrons per square centimeter. And then as you lower the density, you see that the resistance changes by many, many orders of magnitude here, 6, 7 orders of magnitude as you lower the resistance. And this is what you call a metal insulator transition. Now, if you want to diagnose where does the metal insulator transition happen, there are sort of two criteria that you can use. One is you look for where does the sign of d rho dt change. So metals have resistance increasing with temperature from phonon scattering. Insulators have resistance decreasing with temperature that comes from electrons being activated out of some trapped state. And so you can see that here this has negative d rho dt, this has positive. And if you want to look for where the sign changes, it's right around here at about 1.6 times 10 to the 10. Now, another criterion you can use is to look for where the resistance crosses the quantum of resistance, h over d squared, about 26 kiloohms. And that happens right about here. Very, very similar density. I don't want to make this too exact. The sample isn't exactly square anyway. But if you look at those, the point is that if you look at those two possible ways of diagnosing where the metal insulator transition happens, they both happen at about the same density, 1.6 times 10 to the 10, which corresponds to RS equals 30, which is more or less exactly where it was predicted. Okay, the other thing that happens as you cross that critical density, you go from the liquid state to the crystal state, is that you see the IV curve start to look very nonlinear. So, in a good conductor, voltage and current they have a linear relationship between each other, and that's what you see at large density. So you can also take the derivative; it looks pretty constant. On the other hand, when you go below the critical density, this is only slightly below, you suddenly see this IV curve looks very, very nonlinear. So, sorry, these different curves are different temperature. If you just focus on the lowest one, what you see is that there's a region where the current is pretty much zero for a finite range of voltage. So it's as if you change the voltage and nothing happens until you get to a sort of critical voltage where suddenly the current flows. And this is what you call pinning. And pinning is supposed to be a clear. Pinning is a characteristic feature of a Wigner crystal. The idea is that in a normal conductor, electrons can all move individually, but in a Wigner crystal, no electron can move by itself, and your system can only conduct by the whole system sliding together. So if you have any finite disorder at all, individual electrons get stuck in traps, and therefore no electrons can move until you apply such a large electric field that the whole thing can slide out of the trap. So this appearance of a sort of a pinning voltage looks consistent with what you'd expect for a Wigner crystal. Okay, I think I did see a thing in the chat. Okay. Right. So what I should warn you about is that this nonlinear IV curve is not at all, let me say this, nonlinear IV is not unique to Wigner crystals. And in fact, any electrical insulator has nonlinear IV in one way or another. Maybe the most famous version is the so-called Poole-Frankel effect, where you have electrons trapped in potential wells, and the amount of energy it takes to get out of the potential well can be reduced by applying an electric field. So you apply electric field, it sort of tilts the potential energy landscape. And now the energy required to get out of the trap is reduced. And so the conductivity, the IV curve becomes nonlinear. The current depends in a nonlinear way on the applied voltage. I see some questions. Let me just finish this slide and then I'll take them. The other thing I should say is that the existence of this voltage also allows electrons to tunnel through, to quantum tunnel out of the trap. What happens in a typical electrical insulator is that as you in the limit of zero temperature, the current comes from carriers being sort of field ionized. So the electric field allows them to tunnel out of localized states. So even in the limit of zero temperature, you still have some finite current at finite voltage. But the relationship between current and voltage has some sort of exponential form like this that comes from how you change this tunnel barrier with changing voltage. So this is some characteristic data. It turns out it's on hydrogenated graphene. Doesn't matter very much, except that this is a two-dimensional insulator. And the form of this IV curve has some sort of smooth, very nonlinear behavior that has some kind of stretched exponential form. And I want to contrast this with the sort of data that Joe took in zinc oxide. So this is a very low temperature on the insulating side of the apparent Wigner crystal transition. And what you're seeing here is I versus V. And there is very sharp voltages at which the current turns on. So it looks very, very close to 0 picoamps in magnitude until some very sharp voltage. And then the current suddenly turns on, which is what you would expect for pinning of a crystal. Now, the two curves here basically correspond to whether you're sweeping the voltage from low to high or from high to low. And what you're seeing here is a kind of hysteresis. And in fact, it's known that Wigner crystals have this kind of hysteresis and this sharp pinning. So this is data for Wigner crystals in very strong magnetic field. This has been demonstrated before. And our data really looks much more like this than like what you'd expect from just a disorder-induced insulator. Okay, so let me sort of take questions here. I think Vala was first. Vala, you want to ask your question?
Yeah, thanks. Hear me?
Yes, I hear you.
Okay, great. So I just wanted to clarify both whether this data is taken in a 2 or 4 terminal configuration, and also do you see anything clear that says that this is coming from this nonlinear IV curves are coming from an effect of the 2-deg itself rather than something at the contacts?
Okay, the short answer is I'm a theorist and shouldn't ask me hard questions like that. But this is all 4 terminal measurements. And I think Joe was pretty careful to check that it wasn't contact effects. But you should probably direct your questions to him if you have more skeptical ones. Sorry.
Sure.
Okay, Sergio, you had a question?
Yeah, Brian, thanks. So it's actually from a couple of slides back. I was just curious when you're talking about the.
Sorry, you're a little muffled. Would you mind speaking up a little bit?
Oh, yeah, sure. Is
there we
that
go. That's
better?
Better. Thank you. Yep, better.
Yeah, sorry. I had a question from, yeah, maybe a couple of slides back where you were talking about the critical density. Yeah, this slide here. I was just curious, which of these numbers here are sort of material independent, like the critical density and the critical RS value? Are those both material independent or just RS? Which is
right. So the idea is that RS should be some universal number, at least in the ideal limit of like an ideal 2-deg with 0 thickness and so forth. But the critical density N is material dependent. So what matters, sorry if I go back here, what matters is this parameter that has a density in it and this Bohr radius squared. And the Bohr radius is a material parameter. It has the dielectric constant and the effective mass.
Right. Okay. Okay, perfect. Thank you.
Sure. Okay, thank you guys. All right, so let's go on. So if I just summarize, what is the evidence that this thing actually is a Wigner crystal? There are sort of 3 pieces of evidence that come together. One is that we clearly see a metal insulator transition at the predicted value of RS around 30. 2 is that right at this transition, we see that an extremely nonlinear IV relation begins. So it sort of turns on abruptly once you cross from metal to insulator. And all insulators have nonlinear IV, but this really looks like not just nonlinear IV, but the emergence of a particular pinning voltage. And I should emphasize that, it's probably not fair to say that this is a conclusive demonstration of Wigner crystallization. For that, you would really want to see some signature of the Wigner lattice itself, like some translation symmetry breaking and the formation of some periodic structure. And just by measuring resistance, you can't do that. But what we can say is that all these things are what you'd expect from a Wigner crystal. They look consistent. So for the rest of this talk, I want to sort of take as given that what we're seeing really is the liquid to crystal transition at a particular concentration. And from now on, I sort of want to focus on what are the mysteries that are appearing in the data. If you look at the data from this perspective, what about it is unexpected or mysterious? And I want to try to outline for you 5 different mysteries that we're seeing. Okay, I see that Senthil has a question. Go ahead, Senthil.
Yeah, so Shubnik or Dehaas oscillation seen in the liquid side?
Yes, and I will talk about that in the very next slide.
All right, great.
Okay, so let's do exactly what Senthil asked. So I sort of said most of this talk is not going to be about magnetic field, but let me have 2 slides about what happens in a magnetic field. So now this is the magnetic field that's perpendicular to the planes. This is an orbital field, one that has a Lorentz force associated with it. And density on the y-axis, and the color is telling you the resistance. So if you look at it, say up here, this is the Fermi liquid side, and you're seeing these oscillations that turn out to be periodic in 1/b. These are Shubnikov-Dehaas oscillations, like Senthil was asking about. And actually, this plot looks, beautiful and very expected. This is what you call a Landau fan, different lines correspond to different integer quantum Hall states, and you can see them very clearly. So in that sense, it's very nice. But if you look too hard at this, you'll realize there's something quite surprising, which is that, as Senthil asked about, the metal insulator transition is right here. So supposedly, everything up here is a Fermi liquid. It should be able to form quantum Hall states, no problem. But everything down here is an insulator. And presumably, this very nonlinear insulator looks like a Wigner crystal. So, you've got giga-ohms of resistance down here, and still some kind of signatures of what looks like a Landau fan. So just to drive home the point, let me take a line cut right here at some density about, 30% below the critical density, 1.3 times 10 to the 10. And now let me plot resistance as a function of this out-of-plane magnetic field. What you see is this. You see some wiggles that look like the Shubnikov-de-Haas that Senthil was asking about. And then you get the formation of a quantum Hall state, and the resistance, this is rho xx, drops way, way down, 5-6 orders of magnitude. And actually, my understanding is that this 10 to the 2 is sort of an instrumental zero, like it's as close to zero as can be measured by this measurement, this setup. So you're really seeing this drop to zero. And that's something that you expect in a quantum Hall state. You expect that once you get to an integer quantum Hall state, you form dissipationless edge states. The edge states carry current without resistance, and so rho xx drops to zero. But the funny thing about this picture is that, that's a picture that's really meant for a metal. And metals live way down here at resistance smaller than h over d squared. I'm talking about resistances that are 4 or 5 orders of magnitude bigger than that, 10 to the 8, 10 to the 9 ohms way up here. And somehow this state, this insulating state that we think is a Wigner crystal, is forming dissipationless edge states as in quantum Hall. And that's kind of a mystery. Like if you think about the bulk as a Wigner crystal, it's not at all clear how a Wigner crystal should form quantum Hall edge states. In this picture that I told you that every electron is a harmonic oscillator localized in a trap created by its neighbors. If I turn on a magnetic field, it should only, constrict that wave function and make it more localized. And it's not at all clear how you get quantum Hall edge states emerging from this picture. And I think that resolving this mystery will probably require us to think carefully about what's happening on the edge of the sample and whether it's possible for something that's a Wigner crystal in the bulk to have quantum Hall edge states on its sides. So that's mystery number one. I'm not going to give you a proffer an explanation about it. Now, for the rest of this talk, I want to forget about magnetic field, or at least I want to forget about out-of-plane magnetic field, so no Lorentz force anymore. But I am going to talk about what happens with an in-plane magnetic field, an in-plane magnetic field that couples only to the spin of the electrons, and therefore can sort of spin polarize my electron system. Now, everywhere I'm going to talk about pretty small in-plane fields, just a few tenths of a Tesla. So this is quite small, and it's really not going to be able to affect what's happening in the transverse direction. So the quantum well here is quite thin, 5 nanometers or so, and these fields are way too small to affect what's happening in that transverse direction. But they do have an effect of sort of spin polarizing the electron gas that I'm now going to explore. Okay, so the first mystery that appears associated with spin polarization is what happens in the Wigner crystal regime. So we're low density, we're in the apparent Wigner crystal phase. And the first thing you can see, sorry, these curves correspond to different temperature. Just focus on the top ones. Those are the lowest temperatures here. What you're seeing is that as you turn on this in-plane field, you are apparently spin polarizing the system. And after a small field, your resistance sort of changes from one value to another that we think is associated with going from spin unpolarized to spin polarized. And now it sort of saturates at some new value. Now, the first thing you might be surprised by is why the system wasn't spin polarized to start with. If you paid attention to this quantum Monte Carlo diagram that I showed you earlier, it suggested that deep in the Wigner crystal regime, you're supposed to be a spin polarized electron gas, or spin polarized Wigner crystal, in which case an in-plane field wouldn't do anything. I think that that's not so much of a mystery, because deep in the Wigner crystal regime, the system is almost spin indifferent. Like the effective spin enters only through some exchange interaction that's exponentially small. And so the energy scale associated with different spin states, with the difference between different spin states is just really small. It's exponentially small. So even the heroic temperatures that Joe worked at, 10 millikelvin, can be too large to really enable spin ordering. So consequently, it takes just a little bit of magnetic field to give them a reason to care about spin. Then the system sort of reaches this polarized state. But now the remaining mystery is, why did the resistance go in this direction when you spin polarized? So I should emphasize that what I'm plotting here is the ohmic conductivity. So I first showed that the IV curve was extremely nonlinear. It looked like it was almost zero for some wide range of voltage, and then the current suddenly turned on. But it's not literally zero. There's some very small linear slope of I versus V that is strongly temperature dependent. And that's sort of what's being plotted here. So the question is why that ohmic conductivity should depend in the way it does on spin polarization. In other words, why does spin polarizing the Wigner crystal make the resistance go up instead of down? And it turns out that that answer is really not known. And in fact, surprisingly little is known about what is the ohmic conductivity of a Wigner crystal. As far as I know, the state-of-the-art theoretical paper is this one by Klaus from 2004, where he explains that, in a Wigner crystal, your conductivity is dominated by rare disorder-induced defects. So you have your Wigner lattice, but there's some finite disorder potential that creates rare, interstitials or dislocations in the Wigner lattice. And then those defects can undergo phonon-assisted tunneling. So that's Klaus' paper, but this paper doesn't explain why the conductivity should depend on spin polarization and why it should depend in the direction that it does. So I think that's really an open question, is one to sort of flesh out what are the mechanisms associated with ohmic conductivity of Wigner crystal. This is a very nice paper, but probably not the full story. And then once we're confident that we understand that, we can ask the question of why should a Wigner crystal get more resistive when you spin polarize as opposed to less resistive? Okay, I saw a hand raised. Vala, you want to ask your question?
Yeah, maybe this is premature, but I'm wondering if any of these ideas change a lot if your crystal is granular. If your Wigner crystal is granular.
Oh, you mean it has like grain boundaries or different domains or something?
Yes.
Probably they do. Like I said, this question about the ohmic conductivity of a Wigner crystal is sort of terra incognita, so to speak. A lot is not known, and I'm not an expert myself.
All right,
so
thank you.
Probably such defects in the Wigner lattice will contribute to conductivity, but I don't think that that's in any sense a solved question. Okay, so that's mystery number 2. Let's move on to mystery number 3. Now, for the remainder of this talk, I want to focus. So far, I was talking about what happens down here in the insulating state at small n. And from now on, I want to focus on what happens at larger concentrations. So starting in the Fermi liquid state. Sorry, I should orient you to this diagram. This is in-plane field on the x-axis. So 0 corresponds to something that's not spin polarized. And then as I turn on the in-plane field, I go to something more spin polarized. And then there's concentration on the vertical axis. And this is resistance in color. So low resistance up here, high resistance down here. Now, I sort of told you before that there are sort of 2 ways that you can diagnose where the metal insulator transition happens. One is by the sign of rho versus T. And so you can look for where d rho dt changes sign, and that's indicated by this sort of white triangle. Everything in here has metallic-like temperature dependence. Everything outside has insulating-like temperature dependence. You can also look at where the resistance matches H over E squared. That's this black line. So what I want to focus my attention on now is this region over here. So this is where you started with something that's clearly a Fermi liquid. And now by spin polarizing, you sort of passed through both of those criteria, by which I mean the resistance started becoming insulating-like, and the resistance got bigger than H over E squared. So in a super naive sense, this region right here would be an insulator. But I sort of want to make the point that actually this region doesn't look very much like an insulator in the same way that this one does. So down here, we had an IV curve that was strongly nonlinear, as I showed you before, and the temperature dependence is extremely strong. So by changing, say, from 100 millikelvin to 10 millikelvin, you see the resistance change by many orders of magnitude. Up here, on the other hand, the temperature dependence is quite weak, and the IV curve remains linear. So in a sense, this one doesn't look very much like an insulator, even though it sort of goes on the insulating side of both of these 2 tests. And in fact, if you compare to what's expected in the theory calculation, so this is again that quantum Monte Carlo calculation, you get a diagram that looks like this. So this is the same scale of magnetic field and RS. There are no free parameters here at all. And what you're seeing is that what's expected when you're, say, up here and you spin polarize is that you just go from a unpolarized liquid state to a polarized liquid state. So this is spin polarized Fermi liquid, paramagnetic Fermi liquid. So the theoretical expectation is that this is just a spin polarized Fermi liquid. So that's sort of the perspective I want to adopt for the next few slides, is that this region over here is just a spin polarized Fermi liquid. But now we have some questions to answer about it. For example, why is the temperature dependence the way it is? So the temperature dependence is insulating-like, which means the resistance is going down as you turn up the temperature. So now let me plot it in a slightly different way. I'm going to plot conductivity, which is inverse of resistance, as a function of temperature. And now these different symbols correspond to different, these lines show conductivity versus temperature, and the symbols on the left side show where in parameter space it's being taken, basically different densities at complete spin polarization. So here's the highest density, and then as you go to lower density, you see the conductivity increasing more strongly with temperature. But this is a pretty weak increase. This is not what an insulator looks like. This is like, in over 1 order of magnitude of temperature change, you're seeing the resistance change, or the conductivity increase by like a factor of 2 or 3, which is not generally what an insulator does. So one question is where is this coming from? How is it possible to have a metal, a spin polarized metal, that has a temperature dependence that looks like this? And it turns out there's a pretty good theory for a linearly increasing conductivity of a spin polarized metal. And that theory belongs to Zala and Arozhny and Aligner in 2001. They were trying to just calculate the effect of interactions on the conductivity. And what they basically described is scattering of electrons by Friedel oscillations. So if you have some impurity in your system, at low temperature, a Fermi liquid creates Friedel oscillations around that impurity, oscillations of electron density. And now another electrons can scatter off of those Friedel oscillations. And because the pattern of Friedel oscillations is relatively extended in space, that can be a relatively strong mechanism. And now as you turn up the temperature, you sort of, the Fermi surface becomes fuzzy, these Friedel oscillations get washed out, and the scattering reduces. So this is a mechanism by which a conductor can have a temperature dependence where the conductivity goes up with increasing temperature because you're making the scatterers less effective. And the nice thing about their theory is that at complete spin polarization, it has a sort of universal dependence. They say that when your electron gas is completely spin polarized, you should have a delta sigma increase in conductivity relative to its zero temperature value that goes like 2T over T Fermi. So okay, here's the data we have. If we make our best estimate of what T Fermi is at these different densities, this is sort of, these green lines are sort of what you get. So what you can see is that at the highest density, where our system is closer to just a regular Fermi liquid state, the theory matches pretty well. And then as you turn up, as you go to lower density, closer and closer to the Wigner crystal transition, it's less good. And so you say, well, maybe it's not too bad, but it's off by a factor 2 or so. But actually, there's sort of a bigger problem with making this theory comparison. And the problem is that the theory has made certain assumptions about asymptotic parameters. And the big one is that it assumes that the conductivity is large. So it assumes that the conductivity is much, much bigger than E squared over H. And in fact, in all of these curves that I'm showing you, the opposite is true. That in fact, say for this highest density one, the conductivity is 10 times smaller than E squared over H. So this inequality is strongly violated. The other thing that's being assumed by the theory is that the change in conductivity is small. This is supposed to be a small correction to the conductivity as a function of temperature. And you're seeing that, in fact, we're seeing a sort of linear change over a factor 2, factor 3. So it's not at all clear that this theory should work in the regime we're seeing it. So I think it should be considered an open question whether this pronounced linear in T conductivity that we're seeing near the Wigner crystal transition, but on the Fermi liquid side, can be considered an instance of this Zala and Arozhny Aligner theory or not. I think it's not obviously obvious that it should be. Okay, an even bigger mystery that I think that appears in the same region of phase space is that if you start on the liquid side of the transition, and now you start to turn on a spin polarization field, you see just a huge change of the resistance. So remember that as you go from, say, zero field, where the system is presumably not spin polarized, you turn on the field, it saturates. The only thing that you're doing is just spin polarizing the system. But somehow by doing that, the resistance is changing by 2 orders of magnitude. So here is just slightly above the critical density, and you're seeing just a giant increase of the resistance. And it's just very unclear how that could happen. why just the act of spin polarizing your electron system should have a 2 orders of magnitude effect on the conductivity. So you can ask, is there any theory that would predict an increase of resistance with spin polarization?
So sorry, Brian, quick question.
Oh, hi, Ilya. Yeah.
So hi doing. So this plot that you were showing just now, is it still inside that triangle that is supposed to be the Fermi liquid state?
Yes, thank you. Yes, it's still inside the triangle. So this is
All right.
The critical density is 1.6. This is 2. So if I go back to the triangle, sorry, we're here. So I'm starting here. It's clearly above the metal insulator transition, and now I'm applying in-plane field to go. Sorry, I lost my mouse. I'm applying in-plane field to go in this direction.
No, but so how far do you go? I mean, that's the question.
Okay, so you can look at the x-axis here. X-axis is about 0.2, is all the way out. So I'm going from here all the way past this line.
Oh, I see. So, but then you shouldn't be really surprised because you go to the crystal, right?
Well, my interpretation is that what happens over here is not a crystal. This is the region where you see linear T conductivity and linear IV characteristics. Unlike down here, where you see exponential in T conductivity and strongly nonlinear IV.
Okay.
So my interpretation, tentative interpretation, is that this is just a spin polarized Fermi liquid and is not an insulator. So, I mean, you're right. The naive, when you look at a curve like this, you could say, oh, this is a metal insulator transition that's being affected by spin polarization. And you can ask yourself, well, how should that happen? Quantum Monte Carlo doesn't predict that should happen. But I think more consistent with the experimental data is that this is not an insulating state over here, even though it has insulating like temperature dependence. It's just a spin polarized Fermi liquid. But for some reason, the spin polarized Fermi liquid has 2 orders of magnitude bigger resistance. And that's the mysterious part. Did I answer your question?
Yes, thank you.
Okay. So is there a theory that would have predicted the resistance to increase with spin polarization? And the answer is kind of. So the obvious calculation that you can do is just the standard, scattering calculation where you do random phase approximation plus Born approximation for scattering. And this calculation has been done many times in the literature. Okay, let's see. I have a bunch of objections already. So let me just start. Senthil, you want to ask your question now?
Yeah, no, so I'm wondering, so the interpretation is that there's a saturation field, where you think that saturation is associated with full spin polarization.
Yeah, that's the interpretation, that once the resistance doesn't change with in-plane field anymore, that you're seeing spin polarization.
So am I supposed to think that the Zeeman energy at the saturation field is comparable to the Fermi energy of the system?
Yes, that's the idea. Yeah. Okay,
so I wonder whether the numerical calculations tell you what the critical ORS is for the Wigner crystallization for a spin polarized Fermi liquid.
Yeah, so you're talking about the quantum Monte Carlo calculation.
Yeah, I see. So
so quantum Monte Carlo gives a phase diagram that looks like this.
So the ORS is somewhat smaller when you fully spin polarized as opposed to. Yeah,
that's right.
Yeah.
Right. Now, I don't want to take this as gospel or something, but there is that prediction that it should be slightly easier to enter the Wigner crystal phase when you are spin polarized. So, maybe what's happening is that we're here and that you could indeed drive from a liquid to a crystal phase. So we're sort of diagnosing where are you an insulator versus where are you conductor by whether you have an exponential temperature dependence and whether you have strongly nonlinear IV. So what I'm showing here, what I was showing here is a regime where even out here, you have ohmic IV curve and you have a non-exponential temperature dependence.
Good, thanks.
Okay, let's see. Was there another question? Lautaro, you had a question.
Yeah. Is there a possibility that there is a differential cross-section that is spin dependent that is the reason of this drop of the resistivity?
Sorry, when you say differential cross-section, you mean a scattering cross-section?
Scattering cross-section, yes.
Yes, that's possible. So, I mean, that is indeed the question, whether there's a theory that would predict an effect like that. And I sort of wanted to, that was sort of my next slide. So maybe if I don't answer your question in the next slide, you can raise your hand again. Right, so the question is, does a theory exist that would explain an effect that looks like this? And the answer is sort of there is. So the obvious calculation is you just do the standard random phase approximation plus Born approximation for scattering, and that's been done. And what you'll find, the Born approximation is always valid only when you have a small scattering phase shift. And if you assume that the scatterers are charged impurities, you'll find that your calculation, using the Born approximation is valid only when RS is small. That parameter, and we're operating up by RS equals 30, so it's not obvious that it should be valid. What is clear is that in the limit where the calculation is valid with small RS, the calculation says that the resistance should decrease with spin polarization. In other words, it should go the opposite direction of what I just said. And the dominant effect is actually just that as you go from having two Fermi surfaces that spin up and spin down to just one, you raise the velocity of the one, and that raising of the velocity means your electrons get faster, the conductivity goes up a little bit, resistance goes down. Now, if you nonetheless take the calculation to the large RS limit, you sort of bravely use your Taylor expansion without a small parameter, the calculation will give you increasing resistance with increasing spin polarization. And this has been used in the literature to explain, say, data on silicon inversion layers. So there was some data that showed resistance increasing with spin polarization and saturating, and that was compared to this RPA plus Born approximation scattering, plus Born approximation calculation. The problem is that the reason that the calculation is giving you this increase of resistance with spin polarization is that you're assuming that the system is getting increasingly good at screening out charged impurities. So as you move your carriers to one Fermi surface, you reduce their wavelength and you make them better at screening out charged impurities. But the problem is that, and therefore sorry, I said it the wrong way. Anyway, the problem is that in the regime of the calculation where you would get this result of increased resistance to spin polarization, you're assuming that the screening length for charged impurities is much smaller than the spacing between electrons. And this is a sort of a violation of how RPA works, a violation of what you assumed when you described a screening potential. And this is pointed out in this nice review, again, this RevMod Phys review. So it's not clear that it's not clear that the calculation works in any regime where it would give increasing resistance with spin polarization. So here, where we've really pushed it, so the point is that here we see 2 orders of magnitude increase. It's not at all clear that some mechanism like this could give you what we see. And so I think it needs to be considered an open question that's not explainable within the standard RPA plus Born approximation calculation. Okay, I've used a lot of time. I basically just want to give you one more mystery number 5, which is you can look at how the magnetic field required to achieve spin polarization depends on the density. So here what you're looking at is basically the color tells you how spin polarized your system is. So over here where you're seeing orange means the resistance has saturated and nothing depends on the in-plane magnetic field anymore, presumably because your system is completely spin polarized. So over here, at the top of this plot, you're seeing when the density is large, it requires some field to spin polarized. As you reduce the density, Fermi energy goes down. This magnetic field required to spin polarized is going down. But then we see this really funny thing where it sort of bows outward again. And very near the apparent metal insulator transition, there's a local maximum in how much magnetic field is required to saturate the resistance to achieve what we think is spin polarization. And this non-monotonicity is quite puzzling, and we really don't know where it comes from. We tried explaining it in terms of some phase coexistence scenario or something, and we didn't get anywhere. So this really is a puzzle that I don't have anything too smart to say about. Okay, that's really it. So I hope you enjoyed me, broadcasting ignorance at you. But what I really the point I want to make is that there are some real surprises in this system. It looks like a just canonical instance of the Fermi liquid to Wigner crystal transition. But we're seeing in the vicinity of that transition, what I count as at least 5 big puzzles. The first one is an apparent transition directly from a Wigner crystal to an integer quantum Hall state with dissipationless edges. When you apply an out-of-plane magnetic field, it's not clear how to think about that. The transport in the Wigner crystal phase, the ohmic transport is puzzling in general, and why it should increase resistance with spin polarization is not understood. What I'm calling the spin polarized Fermi liquid phase, just above the metal insulator transition, is in general mysterious. There are places where it has large resistance, say as much as a factor of 10 above E squared over H, or H over E squared, and it has this linear T conductivity. Not clear how to understand that properly. We see this enormous increase in resistance with spin polarization, even whilst remaining in a phase that doesn't look like an insulator. And the origin of this huge magnitude resistance is a mystery. And finally, the behavior of the spin polarization field is also mysterious. So with that, I'll just put up the archive reference one more time, and I'll thank you guys for your sharp questions and your kind attention. Thanks. Okay, Anton, I see your hand up.
Yeah, it's probably an irrelevant phenomenon, but I was just wondering if the finite thickness of the 2-deck could play a role here. You said it's like it's thin, but it's not atomically thin. It's like 5 nanometers or so.
Yeah, that's right. So the short answer is it certainly could play a role, and the extent to which it plays a role is pretty unknown. I mean, like predicting where the Wigner crystal transition takes place in terms of a quantitative RS value is tricky. Our best estimate is that it's 30. Accounting for finite thickness could certainly move that. You might expect it to move it to, you might expect that to make Wigner crystallization harder, because you're essentially like fuzzing out the short distance Coulomb and making it a little weaker. So you might expect it to move the Wigner crystal to larger RS somehow. But it's basically, the short answer is it's not known. It's not known in the quantitative level. It certainly could be an effect. We expect it's a small effect because of the large ratio between the inter-electron spacing and the thickness of the wave function. But I don't know.
What about magnetic field though? So with 5 nanometers and a fraction of a Tesla, there's some orbital effect of the in-plane field.
Yeah, right. So what you would want to do is compare the thickness of the wave function to the magnetic length. So once the magnetic length is comparable, so the magnetic length goes like 1 over square root of B, and once the magnetic length is comparable to the thickness of the wave function, then you'd expect some strong effects. But for everything here, the in-plane field I'm talking about is quite small. It's 2/10 of a Tesla. And in that limit, the magnetic length is, it's 25 nanometers divided by square root of a 10th. So you're talking about 75 nanometers. So I expect that such effects are very small. Okay, Senthil, you had a question?
Yeah, so wonderful talk. So you showed the Landau fan, right? So if I just stick to the metallic side, have the experimentalists studied the temperature dependence and to extract the effect of mass?
Okay, my understanding is that all the energy scales here are really small, right? We're at n equals 10 to the 10. And the corresponding Fermi energy, even up here at the top of the diagram, is maybe 100 millikelvin. So now you want to do a temperature-dependent study of transport between 10 and 100 millikelvin or less. My understanding is it's just very hard to do that analysis, given that all the energy scales are so very low. So my understanding is that wasn't possible. Joe, you can correct me if I'm wrong, but that it really wasn't possible to extract the effective mass by Shubin-Haas.
So I've done a lot of these analyses in the past in higher density samples. So we have a pretty good idea of what the mass is doing across a broad range of densities. But yeah, as Brian said, with this specific device, it's very challenging to get reliable thermometry to do those type of analysis to a degree where I'd like to report the numbers. The other issue here is that these Landau levels that you're seeing are fully spin split. Like this is a fully spin polarized gas in like filling factor, you can see 1, 2, 3, 4, 5 here. And if you do such an analysis and compare the mass of the full versus spinless C, in this system and in other systems, you'll see that this mass is different. So it's a little bit difficult to compare apples with apples here due to the experimental constraints. But what Brian didn't show, but is kind of included in the data, essentially, is that what is much easier to study is the product of G and M. The spins, approximately the spin susceptibility, and that comes out of the in-plane polarization critical field, as you said, where the Zeeman energy is approximately equal to the Fermi energy. And we know with relatively high confidence that as that parameter is enhancing, that enhancement comes from the effective mass portion of G and M. We don't see in evidence, any experimental evidence that G is changing through renormalization effects. So from that, we can kind of back calculate an estimate of what the mass is.
Mm-hmm.
Yeah, Senthil, there's a pretty extensive description of what happens to the effective mass in the paper.
Right.
And let me just refer you to that. I didn't talk about it because I didn't have anything smart to say, but you'll see some more things there.
All right, very good, thanks.
Let me also please apologize again for giving a talk that Joe should absolutely be giving because it's his work. I really am doing this just because I wanted to broadcast his results and also save him the work of having to actually prepare a talk. Okay, Sergio, you had a question?
Yes, can you hear me, Brian?
Yes.
Okay, great, thanks. Yeah, I had a question about, I think point number 4, but maybe it could relate to some of the other results. I was wondering if they have a good idea of the sample uniformity, particularly how it might relate to, I don't know, data taken near the transition, the critical density, where maybe the density is not, constant everywhere in the sample. Like, I was wondering if the small resistance increase with magnetic field could be resulting from some portions of the sample maybe going insulating, but other portions are still metallic, and there's some percolating path of metallicity that allows the resistance to sort of saturate once you turn on the magnetic
Yeah,
field.
that's a great question. So I mean, there should be some disorder, like anytime you have any concentration of charged impurities in your material, and we have some, we have an upper bound on them, there should be some disorder modulation of the density. So actually, we don't know how many charged impurities are in the sample. We have an upper bound on it that comes from some, I can't remember, mass spectrometry studies or something. And if you take that upper bound, you can get an upper bound on what the density modulation should be in the electron gas. And it worked out to be about 0.3 times 10 to the 10. So the density of the electron gas could be modulated from one region of the sample to the other by as much as 0.3 in this diagram. So that would be, here.
Mm-hmm.
So it could indeed be possible that some of the features we're seeing in the vicinity of the transition, rely on some disorder modulation of the phase to be understood. And all I can say is that we tried to think about those kind of, spatial modulation and percolation scenarios, and we tried to see if they could explain some of the features that we're seeing, and we're unable to come up with an explanation that worked or was compelling. That doesn't mean it's not at work. Generically, you would expect it to be important near a phase transition. And we spent some time thinking about it and didn't come to anything compelling, is all I can say.
Mm-hmm. Yeah,
it's a very good question.
In fact, yeah, 0.3 times 10 to the 10 modulation is pretty amazing. Right?
Yeah, I mean, this is an amazing system in general, and I feel very glad to have been brought in as a person to think about this data. This is quite an amazing corner of parameter space.
And maybe that makes sense with the perpendicular field data, where it looks like the quantum oscillations occur at a pretty low magnetic field, and I guess that implies there's a pretty high mobility, if you want to.
Yeah, the mobility, as I say here, the mobility is about 1 million, at least at the, when you're not too close to the transition. So up here, it's about 1 million.
Right. And somehow, strangely, it sort of leaks over into the insulating state, which also shows oscillations at pretty low magnetic field also.
Yeah, that would suggest some kind of picture where you have regions that are insulating and regions that are conducting, and how to think about that properly is not known.
It's interesting. Thank you.
Yeah. Okay. Thank you, Juan.
Yeah. Actually, do you expect any phase separation across this Fermi liquid and Wigner crystal state? Like if there is, if there's any Fermi liquid bubbles in the Wigner crystal phase?
Yeah, that's a hard question. There are, as you know, there are different scenarios for why you should get phase coexistence. The most likely one is that you just have this disorder-induced modulation of the density, which would mean that some regions of the sample have slightly different densities than the others. So the ones with lower density would go insulating first, and like you said, make bubbles of Wigner crystal in a sea of Fermi liquid. And then as you move through the transition, you end up with lakes of Fermi liquid in a in a dry land of Wigner crystal. So in general, you would expect something like that very near the transition. Like I said, we tried to make a story about that and couldn't find something in the data that clearly indicated it. But you would certainly expect some kind of phase coexistence like that very near the transition, I think.
Okay, so ideally, if there's no disorder, you just don't expect anything. It's just the first order phase transition.
Okay, that's a hard story too. That comes back to this Spivak and Kivelson story about microemulsion phases, and that's a surprisingly intricate question. I don't want to comment on it too much. Let me just say that if such a scenario is possible, it should exist over a very narrow and delicate range of the parameter space here, and probably would not really be seen.
Okay, thank you.
Yeah, you should know that I'm thinking about that question in more detail, and I might be able to say something smarter to you in a month or two. Okay, any other questions?
Maybe I can just ask one more.
Yeah, go ahead.
So again, it's, I guess, an experimental question. Is it feasible to measure the thermal power?
Oof. Joe, I don't know if you want to comment on that one.
I think so, but what does thermal power scale as? T squared or T cubed or something like that?
Linear in T.
It's linear in T, yeah.
Okay.
It's some proxy for the net that is in several correlated materials. It roughly behaves the same as the entropy per particle.
Yeah.
Okay. So part of anything is possible, yes. What, in my opinion, as an experimentalist, has held partially been a challenge in this field has just been going to very, very low temperatures and probing this physics. As Brian said, the energy scales involved, are really tiny. The kinetic energy here is on the order of 100 millikelvin. The energy differences between the curves in the quantum Monte Carlo simulations is on the order of 50 millikelvin or something. So a good portion of this project was just the cryogenics aspect of it, going to as low temperature as possible. So we think the electron temperature is quite low here, maybe 10-ish or so millikelvin. Applying a thermal gradient in that type of circumstance is not impossible, but it'd be a grad student's PhD project, I would say.
Yeah. Yes, that's
but
the one thing I can
maybe stay tuned. Yeah.
Yeah. So the one thing I can say is that, mostly all the data I'm showing you here is at base temperature, nominally 7 millikelvin, but in fact, maybe a little higher, maybe 10. But if you go up to 30, 40, 50 millikelvin, everything is washed out and the data is just much more boring. Mm-hmm. So it really is requiring very low temperature here. And that's the heroic work that Joe's been doing. Mm-hmm. Okay, any other questions? Well, if not, let's thank our speaker, and thank you guys for coming. I appreciate it.